So this video is actually a response to a question I got to a previous video on the Simmons-Smith reaction. Actually, a couple of questions got asked about. So one, when we have the Simmons-Smith reaction, and I'll draw just our generic alkene here, and we have our CH2, I2 over zinc, and we end up producing two stereoisomer here. So in a lot of textbook answers, what you'll see is they like to put the cyclopropane in plane. This just makes things easier to draw. And what you'll end up with is a mixture of both the wedged, because we're going to end up with a stereocenter here, wedged, and dashed. And this is kind of inherent to alkene chemistry because there's really very rarely preference for one side of the double bond over the other. We end up with just a racemic mixture. Now, in this case, this would be considered same side addition or a syn addition, so we expect not to get, like, if we were, let's say we had an O, well, we can go, let's say we have a CF3 group here that actually introduces some chirality. Got that flipped. So, because these two groups are trans to one another, they're going to have to finish up trans in the final molecule, and that's kind of the only rule with this alkene addition here. So we have the syn and the anti-additions. Those are going to dictate the stereochemistry of the groups bound to the double bond after the reaction occurs. The second question I got to ask is, can you go over the stereochemistry if there's an oxygen on the allelic carbon? So the allelic carbon here is going to be the one adjacent to the, where's my eraser? Adjacent to this double bond. So let's say I have an OH group here, and we'll put some stereochemistry on it. The Simmons-Smith reaction is not going to affect the stereochemistry of this OH group. So if it ends up being a wedge in this case, when we draw it, it's still going to end up having the same stereochemistry in the end. Now, the challenge with this is that it still has to have the same symmetry. And so there's two ways you can approach this, and the two ways you can approach this is you can try to draw this so this way the cyclopropane product is in plane, so what I have drawn up here, or you can draw it so you pretty much preserve the original structure. You're just changing, you're adding the wedges and the dashes to that carbon that's part of the cyclopropane ring. So what do I mean? Well, here I kind of guessed when it goes back whether these are going to be wedged and dashes. But what I can do instead is I can just draw the starting alkene. And again, I'm recognizing I'm going to get both. So this still has the same RS configuration for the alcohol. Now when I want to draw on the cyclopropane ring, I can draw this as a wedge coming out. So there's my ring. And that's going to push both of these down. Push all these down. Or I can draw this as a dash, and that's going to make all of these wedges. So you can kind of see why textbooks like to draw just the cyclopropane as its own plane. Makes it a lot easier to see, but if you do end up having stereochemistry on something adjacent to those allelic carbons, Simmons-Smith isn't going to change that stereochemistry. It's still going to be the same RNS that it was before. The question now is, how do you draw it to preserve that RNS stereochemistry? And my personal recommendation, again, it's a little bit cheating here, is that you can just kind of draw the cyclopropane ring with just this bond, the original alkene bond in plane, that's just a normal line. Draw both your wedged and dash for the cyclopropane ring, and then for whatever is originally bound to that double bond, that alkene, if the ring is wedged, make them all dash. If the ring is dashed, make everything else wedged. And that'll kind of help you preserve the stereochemistry without worrying about losing it when you go to enter your answer.